I'm Rhea.
Hi, I'm Shiva.
I'm Udit, and we are Team B6, the Ragtag Tag Team.
The problem area that our team looked at was that of the inaccessibility of sports tracking technology for smaller sports programs. Movement tracking is an increasingly prevalent tool being leveraged by teams, players, and coaches to improve their game, but also for scouts to recruit players for the next level. This means that teams and players from less funded programs are further disadvantaged without access to this technology. There are many sports tracking solutions available on the market, but cost tens of thousands of dollars and require complex installation, needing both wired networking and power available near the sports field. We set out to build a more affordable, mobile, and wireless real-time location system designed for basketball. Our main system goals were a location accuracy of less than 1 foot at a frequency of at least 7 Hz and a range of 120 feet. These were derived from real basketball player movement and court size. Real-time location systems have two main components, tags and anchors. Tags are mobile and are to be worn by the player, while anchors are stationary devices placed around the court.
The general concept is that as a player moves around, the distance between the tag on the player and each anchor changes. This distance is directly correlated to the time of flight of a radio signal between the tag and anchor, since light travels about 1 foot in a nanosecond. If we can measure these time of flights, we can use the known fixed anchor positions to triangulate the position of the tag. That said, measuring direct time of flights is expensive, requiring 3 messages per measurement. Instead, we measure the differences in the time of arrival of the tag message between anchor pairs. If the anchors are time synchronized, this difference is the same as the difference in the time of flights of that anchor pair. This gives us a set of hyperbolas where the intersection is the tag location. This time difference of arrival approach means the tags only have to send one-way messages by pulsing at a set frequency, resulting in an increased efficiency, decreased cost, and decreased size of the tag. The disadvantage is that the anchors must be accurately synchronized to a common clock, and all data must be backhauled to a common server that does the position calculations.
We also chose ultra-wideband as our wireless communication medium as it was designed for low interference due to line-of-sight blockage. Each anchor has an ultra-wideband radio interfaced to a Raspberry Pi. The Pi backhauls timestamp pulses and communicates with other anchors to synchronize clocks. Due to COVID-19, testing at a real court became infeasible, so we simplified our hardware system design for the purpose of running small-scale tests to inform a simulation program. The simulation program lets a user move around on a court with simulated anchors. Then, at a set frequency, noisy time of flights are generated from the user's position to each anchor. Each anchor reports its reception timestamp to the localization algorithms. The noise is drawn from a Gaussian distribution based on what's observed in the hardware tests. We measure location accuracy by comparing the position estimation from the localization algorithms to the user's actual position. Thus, our primary goal of achieving a location accuracy of under 1 foot remains intact.
As a result of COVID-19, we shifted our hardware focus from integrating a complete system to collecting hardware metrics that could be plugged into the simulation software. Since we aren't deploying this hardware on a basketball court, we eliminated our backhaul network and simplified the approach to only use one Raspberry Pi communicating with all the anchors. I assembled a stationary system of anchors for the data collection. In a stationary system, all our components stay in one place for the duration of the test. This means that we can measure noise as changes or differences in any measurement, as all true values would stay constant in a stationary system. We first ran tests using anchors with unsynchronized clocks at positions equidistant from the tag. We couldn't compare the direct difference in pulse time of arrival since the anchors' clocks were different, so we compared the recorded periods between corresponding tag pulses. The graphs we got from these tests had high variance, but we noticed a clear visual trend, hyperbolic graphs. This indicated that the ratio of internal clock speeds between anchors was a dominating factor in the high standard deviation of measured differences. We implemented a simple time synchronization algorithm. We place a master clock, essentially a special tag, in a fixed location whose distance from each anchor is known and calibrated ahead of time. The master periodically sends out its own internal time to each anchor at set intervals as a frame of reference. The anchors use their local timestamps and master timestamps to calculate a ratio between the local and master clock. This ratio is used to interpolate the local timestamps marked for each tag pulse into the master clock's frame of reference. Now we measure the noise in the time of arrival on a synced clock system. This graph shows the time difference in arrival between corresponding pulses at anchors equidistant at 1 meter from the tag. We see a massive boost in precision, with a mean time difference of arrival of just 1.9 nanoseconds and a standard deviation of 1.7 nanoseconds. We found that letting anchors run for 30 minutes before testing further improved their precision and reduced the variance. This warm-up and time synchronization ensured high precision and low variance at longer distances like 2.8 meters. Even during trials where obstacles blocked some anchors, we never saw a standard deviation in time difference of arrival above 1.5 nanoseconds. This made us confident that the upper bound for noise is 1.5 nanoseconds. We also believe that noise would decrease with scale, as the true time of flight of a signal becomes more of a dominating factor.
For our localization, we tried 3 different methods to calculate the location from the time differences. We used a linear method, a nonlinear method, and a nonlinear method with an extended Kalman filter. The linear method is similar to the hyperbolic equations, except it eliminates the nonlinear term by using a second anchor as a reference, but at the expense of one equation in the system. The nonlinear method uses hyperbolic equations with one anchor as a reference. To calculate the intersection of these equations, we use least squares regression. The extended Kalman filter also uses hyperbolic equations but estimates the location using current location, last location, and uncertainties of the system. Kalman filters consist of 2 steps, the predict step and update step. In the predict step, it takes the current location and velocity and predicts the next location using no additional measurements. The update step takes the predicted location, time differences from the anchors, and a velocity, and uses those to predict the next location and updates the internal velocity with the new value. Testing the different algorithms, we saw that linear localization performed poorly in 4 anchor systems. The reason for this is when the tag is equidistant from 2 anchors, the data from one of the anchors becomes redundant, which is problematic since it's using 2 anchors as reference. Hyperbolic localization performed the best in systems with no noise, but in noisy systems the accuracy drops significantly. The extended Kalman filter performed the best out of the 3 algorithms in noisy systems, and we managed to achieve close to 1-foot accuracy with 6 anchors.
Even though simulating with user input was a good start, we didn't feel as if this was a good representation of real basketball, and while COVID was stopping us from going to the court, we could still bring the players from the court to us. Using a location dataset from the 2015-2016 NBA season, we generated over 1,000 player movement paths, each with at least 500 positions in them. After tuning the Kalman filter and running each of these real basketball player paths through our simulator, we were able to achieve a location error of just under 1 foot. This was quite exciting, but when we went to visualize what our estimated paths looked like, we realized that our paths were much too choppy and irregular to ever look like a real player movement. This told us that minimizing raw error was not the only important measurement of success, but also passing the eyeball test was vital. Now, looking to strike a balance between qualitative and quantitative measures, we post-processed our estimated locations with a variety of filtering and averaging techniques and ran thousands of simulations looking for the best results. Our post-processing techniques ended up being wildly successful. For both 4 and 6 anchor systems, we were able to reduce location error to under 0.8 feet. We were also careful to keep our training and testing data subsets separate to prevent overfitting. As for qualitative evaluation, we are quite happy with our final outputs, but you can be the judge for that yourself. Here are some of our results. Looking forward, we would like to realize our results by building out our original hardware system and testing it on a basketball court. We also think there are 2 key improvements we could make. First, we can eliminate the warm-up time on the anchor clocks by using a temperature-compensated oscillator that does not need to be warmed up and lower our timestamp noise significantly. The other is using IMUs on tags to feed the Kalman filter acceleration and velocity data to help predict our locations of the players better. Lastly, it would be interesting to expand our simulations and testing to other sports, if we can find the datasets. Thank you so much for listening to this video, and thanks to our TA Jackie and our Professor Tamal for all their feedback and advice.